All right, so this is part 3 of gathering tools from sections 2.1 and 2.2. We're going to use all these tools pretty heavily in the next video, the latter part of chapter 2. But I just wanted to continue with the elementary matrices that we had built in the last video. Okay. If you remember, we had a system, an augmented matrix here that looked like, with a bar, and there was an I here, right? Oh my goodness, that's marked up the dining room wall, yay. So we had that. It looked like this was the original matrix A, and we were trying to find what its inverse looked like using row operations. Gaussian elimination on the whole thing all the way across ended up generating, and only it was because A was an invertible matrix that it ended up this way, that this became the identity matrix, and that became A inverse. In the process, we took A and turned it into A1, A2, A3, and A4, right? And I just want to show you that not only by doing the elementary row operations were we able to do that, that's how we were getting those different matrices there, but also we could have done it by using multiplication on the left by each of these matrices. Okay, so I'm just going to demonstrate that over here. As soon as somebody's done with the refrigerator in the next room. Yeah, okay. So let's see. All right, so what we're going to show is that you can get from A to A1 by simply doing this. A1 is equal to E1 times A. Let's see if you believe that. Can you guys see that? Yes, okay. So E1 was that associated elementary matrix. It looked like 1, 0, 0, 0, 1, 0, negative 1, 0, 1. And when we multiplied it by the matrix A, the original matrix A, which was 1, 0, 1, 0, 1, 0, 1, 1, 0, we end up getting, we end up getting what? Well, let's see. When you have 1, 0, 0 going across, that just picks up the first row, doesn't it? 1, 0, 1. This one, we'll just pick up the second row. 0, 1, 0. Now, notice how multiplying by this third row, that negative 1 is going to multiply across times that first row and add nothing from row 2, but everything we see in row 3. So that's how it does that row operation. So if we do that, we get negative 1 plus 0 plus 1, 0 plus 1 plus 0, and negative 1 plus 0 plus 0. That should be A1. Let's check. 1, 0, 1, 0, 1, 0, 0, 1, negative 1. Okay, and so on. A2 will just be equal to, if you remember, when we did the second row operation over here, we were performing not on A, but on A1, right? So to find A2, we're going to take the elementary row matrix E2 and multiply it by A1. Mind you, that's the same thing as E2. What was A1? It was E1A. Okay, and so on. In the end, we're going to have, after, let's say, I don't know, P row operations, we're going to have something that looks like the last elementary matrix times the one that came before it, all the way down times T times 1 times A. So that last matrix, which, you know, if we're doing Gaussian elimination, like we were over here, if we're doing Gaussian elimination, well, that would be what we were calling B before, right? So I'll just put B. B, where A and B are row equivalent matrices, have same solution sets, remember? Okay. Well, let's see. So you could test this on this one here by checking using your E1, your E2, your E3, your E4, and multiplying them in this order. First we did E1 on A, then we multiplied that by E2, then by E3, then by E4. The assertion is, you can check, taking these matrices multiplied in that order, that's an E, not an F, that you should get that last matrix, which was the identity. Check that this is so. Okay. One other thing I want to add is that each of these elementary row operations, I was talking about last time, each of the operations themselves are reversible. So that should be it should be no surprise that each of these matrices, all the elementary matrices, are themselves invertible, right? So suppose En switches rows. Let's say it switches rows I and J, right? Then what would be its inverse matrix? What would be the matrix that would undo that? We'll switch them back, right? So En's inverse is going to be En itself, because it switches, multiplying by E sub n, switches rows I and J again. So if you switch them one way, now you just switch them again, you've undone that matrix. So that's the easiest type of elementary row operation and elementary row matrix. What's another one? Multiplying by a scalar. So suppose Em multiplies row I by a scalar C that's not equal to 0. What would undo that? The inverse operation that would undo this would multiply that same row I by 1 over C. And you'll notice that that's well defined since C is not equal to 0. Okay. Easy enough to come up with an elementary row operation that does that. Third, this is the trickier one, right? Let's move this tricky one. Suppose ER, let's say, again, I'm going to describe it is equivalent to doing this operation. To describe it, I don't use English so much as that notation. Suppose that's equivalent to new row J equals old row J plus some C times row I, where C does not equal to 0. Okay, so that's that that's the most intricate type of row operation. Suppose this elementary matrix does it. What would undo that? Well, let's see, that would have to be, again, new row J. I'm going to put that one back, right? So it would be equal to the old row J just been switched. And adding to it negative c times rho I. By old row j in quotes, I mean this one. If I want to get back to the original old row j, well, to this, I should subtract off that, right? Well, that's an elementary matrix. So this is going, if we perform this operation on an identity matrix, that's going to give us ER's inverse. So all the elementary matrices are invertible. This is good news, and we're going to use that. This is finishing that argument that all elementary matrices are invertible. Going to use that quite heavily as we go through section 2.3.